Hi everyone, this is a problem with capacitor with dielectric. So this is a capacitor, it's a parallel plate capacitor, but with dielectric. There are two dielectric material. It's kappa 1, which is 1, and the kappa 2 is a 5 dielectric constant. Across this capacitor, a 200 volt is applied, and the area of this capacitor plate is 1 meter square. Now they ask to find out the voltage across each dielectric of the capacitor. So that's meaning how much is going to be the voltage is applied over here across the dielectric constant kappa 1. I should say this is actually the V1, and how much voltage will be applied across the dielectric constant kappa 2. This is they are asking to find out. Now it is obvious from this figure, this 200 voltage actually going to be the divide across these two different capacitor. We can consider this as two different capacitor with the two dielectric material. If I simplify this diagram, is like with that. Say this is my 200 source voltage. Say this is actually that capacitor 1, and this is will be the capacitor 2. It will be act like in that way. Say I can say this is actually the C1, and this is basically the C2, and this is actually your 200 voltage source. So you can consider, or you can draw the equivalent circuit of that one is this. Fine. Now we can say from this diagram, this C1 and C2 basically in series connection, right, with respect to that two node. So that means this 200 voltage is going to be the divided across these two capacitors. How they will divide it, that's we are going to find out in this over here. Fine. So to find out that one, we can write down this equation. Say that electric field equation for this inside that capacitor we write, which is V by D, right? Or you can say that V would be E into D. I know that the separation these two capacitor, the D for kappa 1 would be the 3 millimeter, and D for kappa 2 would be the 1 millimeter. So that's mean I know this D. I have to find out this V for each capacitor. I can write, say, for capacitor 1, for capacitor kappa 1, I could write this with the V1 equally E1 D1, and V2 would be E2 D2. It will be right. So the electric field would be different because your dielectric constant is different. So that's mean if I could find out the electric field between two different capacitor, then I'll be able to find out the potential difference, whereas D1 and D2 is known to me. So this is basically our working formula. So find how I'm going to find out that electric field for the parallel plate capacitor with the dielectric. That I know, say that the electric field for that parallel plate capacitor, actually we know that this is sigma by epsilon naught without dielectric. If you include the dielectric, then you have to add the dielectric constant, right, the denominator. So fine. Then this sigma, which is the surface charge density, so that's mean charge per unit area kappa 1 epsilon naught into A, which is the charge across each plate. So then that charge we can write Q will be actually the C equivalent and V equivalent divided by kappa 1 epsilon naught into A. Why write down the Q equivalent? Basically the charge, since they are in series, this charge is going to be the same in both capacitor. right? So this is would be my working formula over here. So E1 would be to find out the electric field. I will write down the C equivalent, V equivalent divided by kappa 1 epsilon naught into A. This is for electric field to find out that E1, and same way we can find out that E2 would be C equivalent, V equivalent divided by kappa 2 epsilon naught, and the plate area is equal, right? You can say that E1 and E2, that's the same. So that's why I didn't write down the E1 and E2 separately over here. Fine. Now my next job to find out that equivalent capacitor over here. So now we can find out that equivalent capacitance. What would be that? It is basically that in series. So that's why series equivalent capacitance we can write 1 over C1, right? They are in series. So basically, so that's why I will write over here. So that should be 1 over C1 plus 1 over C2, or we can simplify this. C equivalent would be basically C1 C2 divided by C1 plus C2, right? So this would be my equivalent capacitance. Now how am I going to find out C1 and C2? We know that parallel plate capacitor for capacitance is epsilon naught A by D, right? Since they are with dielectric, I have to use the dielectric constant over here, so kappa 1. Same way we can find out the C2 would be kappa 2 epsilon naught A divided by D. D means you can say that this is the D1, you can say this is actually the D2. Now I know everything. I'll be able to find out kappa. I know the kappa 1, epsilon naught is a constant. I know the D1, I know the A. Then I could be able to find out the C1, C2. If I could find out the C1, C2, I'd be able to find out the C equivalent. If I able to find out the C equivalent, then I'd be able to find out the E1 and E2. If I could find out the E1 and E2, I'd be able to find out the V1 and V2. That's the question they are asking in this over here. Okay, fine. Let's start. So I can find. So this using that formula, C1 would be kappa 1 is basically 1. So epsilon naught is 8.85 into 10 to the power minus 12, and the area is 1 meter square divided by D1. So D1 is basically the 3 millimeter, right? So 3 into 10 to the power minus 3. So that will give you 2.95 into 10 to the power minus 9 farad. Fine. So this is the C1. What about the C2? C2 would be dielectric constant is the 5. So into 8.85 into 10 to the power minus 12 divided by separation between the two plate actually that 1 millimeter. So 1 into 10 to the minus 3, and the area is 1. So that will give you 44.25 into 10 to the minus 9 microfarad. Now the equivalent capacitance. Now the C equivalent would be basically using that formula we will need to find out the C equivalent. C equivalent would be 2.77 into 10 to the minus 9 farad. This is my C equivalent because they are in basically in series. So series connection for the capacitor would be 1 over C1 plus 1 over C2. Fine. How I find out the C equivalent? Now I need to find out the E1 using that formula, which is that one, and E2 using that formula. Then I'll be able to find out the V1 and V2. So now, so E1 would be C equivalent, V equivalent divided by kappa 1 epsilon naught into A, which is actually C equivalent is 2.77 into 10 to the power minus 9. The V equivalent is the 200 volt divided by kappa 1 is 1 into 8.85 into 10 to the power minus 12, and area is 1, right? So it will give you the electric field is to be 6.25 into 10 to the power 4 volt per meter. So this is the E1. Now what about the E2? E2 will be same formula. So 2.77 into 10 to the power minus 9. V equivalent is 200 divided by kappa 2 is 5. 5 into 8.85 into 10 to the power minus 12 into 1. That's going to be a E2 is 1.25 into 10 to the power 4 volt per meter. So this is actually the E1 and E2. Now for V1, now that's our target to find out that voltage. V1 would be E1 into D1. That should be basically 6.25 into 10 to the power 4 into D1 is a 3 millimeter. 3 into 10 to the power minus 3. That's going to give you 187.5 volt. And V2 is going to be that E2 into T2, which is 1.25 into 10 to the power 4 into 1 millimeter. T2 10 to the minus 3. That will give you the 12.5 volt, right? That consists in 187.5 plus 12.5 is going to be the 200, because this 200 voltage actually going to the divide across these two capacitors. So this will be the answer of this one. So voltage across the capacitor, or that's mean dielectric constant kappa 1 would be 187, and across that kappa 2, which is the 5, would be 12.5. That's going to be the divided across this capacitor. Okay, fine. Thank you very much.